Today I want to take you on a journey that begins more than 2,000 years ago under the starry sky of Babylon to reflect on a fundamental question in AI. And the question is, in AI, do we only need data or do we also need models? I'm Sergio Barbarossa, I'm an engineer, I work in machine learning, and this is No White Strawberries. Imagine you are a Babylonian astronomer. At night you observe the skies, record the positions of planets, stars and eclipses. Thanks to centuries of observations, the Babylonians were able to predict with great precision where, for example, Jupiter would be in the coming months or years. But they didn't have a physical model. They didn't know why Jupiter moved that way. They obviously had no concept of orbits or even the laws of universal gravitation. They used the data to build predictive tables, but without necessarily having an underlying explanation. And then the ancient Greeks arrived. They observed the same skies, but they asked themselves a question: why does this happen? And so geometric models were born, the celestial spheres, perfect circles, epicycles. They were imperfect, of course, but they introduced an idea, which I would call revolutionary. The world can be understood through abstract models. Today, in artificial intelligence, we are faced with the same dilemma. On one hand, there is the so-called data-driven approach, like with the Babylonians. This approach consists of collecting enormous amounts of data, training complex statistical models such as deep neural networks, and using them to predict the future. On the other hand, there is the model-based approach, the approach based on models like the Greeks used. This approach consists of building mathematical, physical, or causal models that explain the phenomena we observe and allow us to generalize beyond the observed data. The data-driven approach has led to extraordinary results. We see them every day with language models like ChatGPT. All artificial vision systems, speech recognition, they work precisely because they learn from data without necessarily having prior knowledge. In the end, it's like the Babylonians. They observe patterns, extract correlations, and use them to predict outcomes. But what is the risk of acting this way? The risk is that these models, no matter how powerful, don't really know why things happen. Just like the Babylonians, they can tell us where Jupiter will be, but they can't explain the laws that govern the motion of the planets, and so on. The model-based approach, on the other hand, builds intelligence based on physical or mathematical explanations, or ideally causal laws. That is, it can extract the causality behind the phenomena we observe. For example, in robotics, a physical-mechanical model of the body helps to control it better. In a telecommunications network, having channel models helps us better understand how to transmit data through that channel. In medicine, yes, there are algorithms to predict a diagnosis from data, but it's clear that if we also use models based on human physiology, we can provide a much more reliable answer. Models offer explanations, they are able to generalize, and therefore they are more reliable. But there is another fundamental principle that is often forgotten in the era of big data, and that is parsimony. After all, even a neural network is a model, but it's a model that has an incredibly high number of parameters, the coefficients of the so-called neural network, hundreds of billions of parameters, and now we're moving towards trillions of parameters. And what is the point? The point is that the best models are not necessarily the most complex ones with the most parameters, but generally those that can explain and predict with the fewest possible assumptions. This is what is known in philosophy as the principle of Occam's razor. If there are two possible explanations for a certain phenomenon, the explanation we prefer is the simplest one. In statistics and in machine learning in particular, this translates into preferring models that are simpler and therefore more interpretable and with fewer parameters, provided of course that they predict just as well as more sophisticated models. But why do we want simpler models? Because parsimonious models generalize better to data never seen during the learning phase, they are more robust to noise and, above all, they are easier to explain and validate. The so-called explainability problem that we face today in AI, especially in critical environments where we don't want to make mistakes, such as in medicine, finance, and so on. If we combine these two approaches, model-based and data-driven, the truth is that there is no single choice. Today, the frontier of AI lies precisely in trying to integrate data and models. On one hand, there are the so-called physics-informed neural networks, which effectively combine fundamental physical laws with learning from extensive data. Then there's the so-called model-based reinforcement learning, where an agent learns a model of the world in order to plan better, making use of known models of the reality it deals with. And then there is the so-called neurosymbolic AI, which integrates the flexibility of neural networks with symbolic logic. In neurosymbolic AI, there is both the artificial neural part, which obviously tries to mimic the neural networks of our brain, and a symbolic part that uses logical representations, ontologies, and knowledge graphs to try to reason, explain, and manipulate abstract concepts in a structured and, above all, interpretable way. And so, in conclusion, if we go back to the Babylonians, they were extraordinary at predicting the sky, but without a model they would never have understood gravity or, for example, heliocentrism. Today, if we were to build AI solely on data, without models, in some way it would be like returning to a Babylonian intelligence, capable of predicting but incapable of explaining. The real challenge then is to build an AI that combines the precision of the Babylonians with the abstraction of the Greeks. An AI that sees the world, but above all understands it.